In this presentation I will solve a simple problem that illustrates how the frequency response function matrix can be used in practice. So let us suppose now that we have a system that is observed in 2 points, point 1 and point 2. And also suppose that we have done some preliminary measurements. First we apply a 1 Newton excitation force at 25 Hz in point 1, and the response to this force is in point 1. The acceleration, the complex acceleration is 0.50 meters per second with a phase angle pi/3. And in point 2, the complex acceleration has a magnitude 0.15 meters per second square, and the phase angle is minus pi/6. If we apply the 1 Newton excitation force to point 2, we get the responding acceleration in point 1 with magnitude 0.15 meter per second square and phase angle minus pi/6. And in point 2 we get the acceleration response with magnitude 0.45 meter per second square, and the phase angle is minus pi/4. All these phase angles are of course relative to the exciting force. One can also note here that the sort of cross terms, that is the response in point 2 to a force in point 1, is exactly the same as the response in point 1 to a unit exciting force in point 2. This is what is called in physics reciprocity. So the reciprocity principle derived by James Clerk Maxwell means that the frequency response function matrix is symmetric in a case like this. Okay, so the task now is first of all to determine the system's frequency response function matrix at 25 Hz. And secondly, to determine the system's velocity response to a force that can be written, well, in point 1 the force magnitude is 2 newtons and the phase angle is 0. That is, we use this force as reference, time reference. And in the second point, F2, the magnitude is 1.5 Newton and the phase angle is minus pi/4. And of course it is, the frequency of the exciting force is 25 Hz, otherwise we cannot use this information. So, how can we solve this? Well, first of all, we have to discuss how the frequency response function matrix is defined. And as we know, it's a vector matrix relationship looking like this. But if we expand this to two explicit equations, in this case when we have a 2x2 system, then it can be written in this way. So if we, for instance, want to determine the frequency response function matrix element 1, 1, then we have to set the force F2 equal to 0, so that this term, this contribution, disappears. And then the H11 is simply the ratio of the acceleration in point 1 to the force in point 1. And if we want to determine the H12 case element, then we have to set the force F1 equal to 0 so that we can disregard this term. And then in the same way as before, we take the ratio of A1 to F2 to obtain the H12 element. So in general, we must make sure that the exciting force Fk is 0 for all forces, all degrees of freedom that we do not consider. And then the frequency response function matrix element Hmn is the ratio of the responding acceleration over the exciting force, the single exciting force that is non-zero. And this is exactly the type of information we have in this case. So the H11 element at 25 Hertz is the given acceleration, complex acceleration at 25 Hertz, which was this, over the exciting force, which was 1 Newton. So this is the result. And in a similar way, completely similar way, the H21 element is this. And the H12 is this. And H22 is this. So the model, excitation path response model, can be written in this way. We have the response, the acceleration response in point 1 and 2. We have the frequency response function matrix describing the path. And we have the exciting force. And with numerical values for 25 Hertz inserted in the frequency response function matrix, we have this model. So in this case, the second part of the task, to calculate the acceleration response to this force, where we have 2 Newton force in point 1 and then 1.5 Newton force with phase angle minus pi over 4 in point 2, is simply the product of the frequency response function matrix with this exciting force. And performing the matrix vector product in a standard way, the matrix rho multiplied with the vector, with the column vector like this, gives the first element, and the second row multiplied with a column vector gives the second element. And then if we convert from Cartesian form to polar form by using Pythagoras Satz, Pythagoras theorem to get the magnitude and the arcus tangens of the imaginary part, this, over the real part to get the phase angle in radians, we get this result. And this part is of course the acceleration amplitude, the peak value in point 1, and this is the total acceleration peak value in point 2. And then of course we have the phase angles here, which represents the time lag. If we want to convert them to the velocity response, as was question 4 in the task, then we have to time integrate the acceleration response. And in the frequency domain, time integration corresponds to division with I omega. And I omega is of course dividing with I 2 pi times the frequency. So we simply have to divide both acceleration response components with 1 over I 2 pi to 25. And the I here in the denominator we can convert to polar form by considering that 1 over I is minus I, which is in the polar plane, has length 1, magnitude 1, and angle minus pi over 2. So hence the minus pi over 2 in the exponential here. So this is the result, the velocity response in points 1 and point 2, the magnitude and phase angle. The interpretation is as usual, and you take the absolute value and phase angles, and from the phase angle you can calculate the time lag with respect to the excitation, of course. And in this case, since the excitation is the same for both cases, you can calculate the time lag between the velocity components v1 and v2. And as you can see here, blue representing the response in point 1 and green the response in point 2. You can see that the amplitude, the peak values, is almost the same, as you can see here. And the phase angle is, as you can see here, almost 2 pi 1 radians, corresponding to slightly more than pi half. So let's say about, slightly more than pi half. And that is possible to see here. That, well, if the phase shift were pi, then this would be shifted to be in opposite phase. So this peak would then coincide with this valley here. But now, and if it were exactly pi over 2, then this peak here would coincide with this point where the green curve is 0 here. But now it's slightly more, so it's somewhere between pi and pi half. And in this case, the time shifts relative to the force, exciting force F1, is 4.5 milliseconds and 18.1 milliseconds for the two responses.